back again with a short introduction to the quantitative aspects of how we're going to start to calculate the effects of compliance, distensible vessels, on flow and pressure and volume and all these quantities. So this will just get us going, but it's enough to get you through the homeworks this week and start to move you into that slightly more complicated domain of calculations when we have a time-dependent scenario. We went over it qualitatively in the previous video, so please make sure you've seen that. And then, or now, we can actually get into the quantitative parts of it. So one of the key things that we'll use again and again are schematic diagrams. And we'll get into this in even more detail in the next videos, that the schematic diagram that we'll have for a blood vessel will have to contain resistance, because we know it's got resistance. If it's got a radius and all those things, it'll have resistance. But we also know a compliant vessel has compliance. So we have to include a compliance term. And for the resistive part, gee, guess what? We use the resistor. Our schematic element is the resistor. For the compliance part, that may not be quite so obvious. For the compliance part, the schematic element that we use in our schematic diagram, or electrical diagram, is a capacitor. Because a capacitor, as we will see, has many similar features to a compliant vessel, to the pure compliance of that vessel. So the same vessel will have resistance and compliance. We have to pull those terms apart mathematically, and so we include them separately in the schematic diagram. And we include them in two resistors. We break the resistor apart. There's even a simpler one with one resistor and one compliance. This one's a little more dynamic, a little more realistic, where we have, you can picture this as the resistance in the front part of the vessel and the resistance in the back part of the vessel. And then the middle part, where all the distension happens, that's what is captured by the capacitor. So that's the basic building block we'll see again and again. And now we have to observe a conservation law, really important conservation law that we'll use again and again. And that's conservation of flow in this case, which is kind of a reflection of conservation of volume. The blood's not going anywhere that we can't keep track of. These are not leaky vessels. They're not ruptured. They're not cut. So the blood has to go somewhere in those scenarios. So the way we picture it is, whatever flows into the left has to either flow out of the right, so whatever goes into the vessel has to flow out of the vessel, or it extends or distends or expands the vessel. It's as a function of its compliance. So that's like the charge that builds up on a capacitor. That's what I meant by this parallel perspective between a compliant vessel and a capacitor, between a mechanical quantity and an electrical quantity. And so what we have here is the flow that goes in can split. Part of it can go to charge up the compliance of the vessel. Part of it can expand the shape of the vessel, increase its volume, and part of it will flow out. But they have to all equal the same. They can't go anywhere. There's got to be no net gain or loss of flow. So if you see the scenario here, we have 3 liters per second, totally imaginary number, flowing in on one side and 2 liters per second flowing out on the other side. What does that tell you? Qualitatively, it tells you there's more flowing in than flowing out. That's that scenario we just described qualitatively. But now we have numbers. We can capture that in numbers. In fact, from that diagram and those numbers, we can actually figure out what Q3 has to be equal to. It's a simple calculation because flow is conserved. And of course, you see now that it's 1 liter per second. 3 comes in, 2 go out the right-hand side, and 1 goes into the capacitor, into the compliant vessel. So that's how large Q3 is. And because the way we've drawn the arrows, it's a positive number. If I'd drawn the arrow the other way, it would be a negative number. And that we'll get used to with time as well. So it's a positive number, which means the flow is going into the compliant vessel, make it bigger, which makes sense, because we know that the inflow is bigger than the outflow. Okay, so that's conservation of flow. And we'll see that again and again. We should ask ourselves always with these things, just like we're going to ask ourselves when it comes to current flow in a capacitor, is where does the flow go? We always have to make sure we recognize the flow is not leaking out of the vessel. The vessel is waterproof or bloodproof. So the flow is actually just accumulating in the vessel and expanding the diameter of the vessel. That's where the flow goes. And we can calculate how much flow that is because of the difference between inflow and outflow and what change that brings about in volume and pressure, because we're going to know the compliance. And so we come to these few equations that are going to get us started and get us through the homeworks this week. The first of them is really our definition. We've seen this before. It's the definition of compliance as the ratio of change in volume to change in pressure. You can rewrite that, of course, and you can say, how much will the volume change? Well, it'll change by this much capacitance or compliance as a function of the pressure change. We can write that as a straightforward relationship. That's a trivial manipulation. We can then look at that and say, well, delta V, that's the difference between the new volume and the old volume, right? The old volume was the volume that was residual. That was the volume we had with no pressure, right? The vessel doesn't collapse. Most vessels don't collapse automatically when there's no pressure. So it has a residual volume. So that's the V res. And we can say that the volume of a vessel segment is always going to be equal to that residual volume, because that's as low as it will go, plus whatever volume we gain because of a change in pressure. So that's why P new, or this new pressure we have from 0 multiplied by the compliance, tells us what the new volume will be. And we'll use that equation in the homeworks this week already. We can rewrite that again, of course, simple algebra. We can put the new pressure on the left-hand side and say that the ratio, or the new expression we have here, is the difference between the new volume and the residual volume divided by the compliance of the vessel. And we can use these simple equations applying to the conservation laws that you've already heard to describe what's going on. We can write an expression like this and say the change in volume in the vessel, we've described this qualitatively before, here's the quantitative. We can see a change in volume in the vessel like that is going to be a function of the difference in flows, naturally, and the increment of time at which that difference in flow arises. Now you can already picture, because we have a time-dependent scenario here, that initially blood flow is going to go up on the Q1 side, the left side, but eventually Q2 will catch up. So we have to look at this in little time slices and say, in that little time slice, we got this much difference in flow and this much time, this is how much volume we gained. And we have to follow that along through time until we have the two flow rates being the same again. Because as long as they're different, we're incrementally adding to the volume. And this sounds like calculus, and sure enough, we'll use calculus to describe it. But like calculus, we can think of it in a simplified way as little deltas instead of the d's, instead of the actual derivatives. And so these are incremental changes in volume brought about by a difference in flow at that increment, at that instant in time, multiplied by the increment in time at which those Q1 and Q2 are approximately constant. And that's how we can figure out the incremental increase in the volume that we get. And we're using the fact that we have a net flow. We've used that net flux notion before. This is the same thing. It's the difference between Q in and Q out. And so we can rewrite this as change in volume is the net flow times the incremental time at which that net flow is not 0. And that allows us to build equations, solve problems. They're simple equations. Usually it's the figuring out which equation fits where that is the challenge in the homeworks, and that we just have to do through practice. And we'll get practice in that. We can also get to a real calculus expression through a simple derivation. We can start from what we're calling the differential form of this expression, where here we have, again, our compliance law rewritten slightly, delta P on the left, delta V over C on the right. That's just a simple manipulation. But conservation, as we've just said, dictates that we know something about delta V. We know delta V is equal to Q net times delta T. Remember, we just proved that. So we have that expression, which we can then plug in to the first expression and get this new expression. And then we can take the delta T over to the left side, and we can say delta P over delta T equals 1 over C times Q net. And when you see delta P over delta T, you should see where we're heading. Because we're going to say, what happens if we make delta T really small? If we go from a delta T to a dt to an incrementally, tiny incremental, infinitesimally small dt and an appropriately small dp, and that allows us to write down a very simple, actually differential equation. And that sounds terrifying, but this is the expression that we will use to determine how pressure changes as a function of time, because we know its rate of change with regard to time on the left side, and on the right-hand side, we know what determines that, the Q net and the C. And that gives us the starting point to eventually write down a solution for this simple differential equation, which is going to be, guess, an exponent. So we're going to see exponential solutions, just like you saw in Calc 1, Calc 2. And we're going to use those to actually describe how pressure changes as a function of time. And we're going to apply that in little systems, and eventually we're going to apply it in the entire cardiovascular system in your major project so that you can predict how does pressure change as a function of time throughout a heartbeat under different conditions. And the conditions are going to be reflected in things like the compliance value or the resistance values, as we'll see shortly. So that's the starting point. It's enough math to get you through the homework assignment this week. We'll come back and add more to it, of course, shortly, but that's enough to get you going. I hope you have a good time with the homework assignments, as much as that can be a good time. As usual, use the discussion boards, ask questions, we'll get you through it. Thanks a lot for your attention.